All right. Yes, ma'am.
Why are f of x and h of x negative x squared and x squared?
It was built off of the fact that this goes between -1 and 1. So if I had a function that was, like I said, arctangent, or let me write this the way we're used to. X times inverse tangent of who cares? Then what can I make that be between? Yeah, inverse tangent is between -π/2, x, π/2, x. And then I could attack it the same way. Now the limit is x goes to 0, it'll be 0 and 0, so that would have to be 0 at 0. Cool, I like it. I like it. That's enough of that. That's enough of that. Because series theorem does show up every now and again, but it doesn't show up like a ton yet. Alright, let's squeeze theorem. Make sure I didn't leave anybody out. Cool. Alright. Yeah, you're good. Let's see if there's anything else weird in here. What do you think you do? Yeah, here's a good example of another form of indeterminate stuff here. What is that, John? There it is. I like this problem. I would like this problem. So what form is this in? Beautiful. This is infinity minus infinity, which is so desperately not 0. Because one infinity is not equal to another infinity, right? So just give you an example. What you got, Jeff? I don't know, Jeff. Like, if I compared those two, which one's going to infinity faster?
X squared.
Yeah, and that's why the limit as x goes to 0, this would be infinity. Now, of course, we could just kill an x. Are you with me? But then I got this, and that, of course, is pre-calculus. This is pre-calc level. The higher degree's on the top, so it's going to infinity. But it's really because it's going to infinity faster than this one. So they're both infinity in the limit. This is not a bigger infinity. It's just getting to infinity faster. That's why it leaves this guy in the dust, and that's why the answer ends up being infinity. Let me stop there for a second. This idea of how quickly a function approaches infinity or 0 or whatever, that's going to factor in huge. Some of you guys might know something called L'Hopital's rule already. Do not apply that damn thing until we officially learn about it. And even then, only in sections after that one. Right? So don't be all excited that you know it. Don't be showing me that shit. You don't know it officially. So this is infinity minus infinity, which is not necessarily 0. I can't just say that. I don't know what the hell it is. Which one's bigger? Which one's faster? I don't know. Shit. So what can I do? Yeah, I can combine them. So again, it's this general idea of algebraic manipulation if you have something indeterminate. I can factor if I can. I can multiply the conjugate if it has one. I can combine two fractions. So this will be, what does this need? Yeah, this is t times t plus 1. So this needs a t plus 1. Minus, and this guy just needs nothing. So this is already a 1. Is that cool? So then I get limit as t goes to 0 of t over t squared plus t. And now what did I say earlier? Very often it's indeterminate for the same kind of reason, the top and bottom. Once I get it as a ratio, look what happens. What does happen? I don't know. Shit.
So you can
factor out of t. Factor out of t. So t comes out, t plus 1, and cancel that t. I get 1 over t plus 1. So as t approaches 0, that equals 1. Let me let you absorb that for a second. Indeterminate forms are indeterminate for a certain reason. And very often it's that same reason that they're indeterminate. So eventually that similar thing is going to cancel somehow. So then you're able to just plug the value in. Alright. Getting restless out there.
How do you get from t over t squared plus t to...
Oh yeah, so cool. I like there. All right, good. Yes, sir.
So one of the values.
No.
Approach the limit.
As t goes to 0, so I plug a 0 in and I get 1.
Yep.
So 1 is the output of this function at, or 1 is what it looks like the function is approaching as t is going to 0. Good. Limits are stupid important. That's why we spend so much time right now to talk about them. How many guys are going to take out 2? Oh, limits. Oh, all of chapter 11, which is like 11 sections, will involve limits. So understand them now, and you'll be ahead of the game. All right. So I want to get a little bit, I want to get the idea of 2-4 in your brains, so that next time we can really get into it. Maybe I'll give this out next time. But let me show you an example. So 2-4 is where we step back and we say, well, I might need this. I will need this actually, Jeff. Cancel. Any other button. Where's the any other button? 2-4 is where we start to try to formally define this idea of near, this idea of what the hell is a limit really, what's truly going on. And I hate that some professors skip this section. We're going to do this section. Some of you guys are going to be like, which professors skip this section? Can I go there? But what's important is if you're going any further in mathematics, this is like your first baby steps introduction to what proofs really look like. So if you've done geometry, like I've done proofs. No, you haven't. You haven't done shit. That's make you feel bad, but it's just the way it is. So I don't understand why people skip this. If they don't understand themselves, they need to step back and teach themselves. So 2-4 is about the precise definition of limit. So what's really going on then, when I say the limit is x goes to a, and actually let's look at a concrete example. And we're going to study some things that are kind of silly because the process of proving it is difficult enough. So I want something really simple to look at. So let's look at a specific example. For example, what's the limit as x goes to 1 of x squared? Let's do it. Let's do square root of x minus, you can do it, Jeff, x plus 3. That's exciting.
2.
That's crazy, right? So this equals 2. What does that really mean? Well, let's look at that in the calculator. And let me say this again. I'm going to have to say this a few times as I go through this. That is unbelievably obvious. We are using an unbelievably obvious and easy thing to talk about something a little more complicated. We do this in math a lot, but students sometimes are like in the middle of it, they're like, why are you doing all this shit? I know it's 2. Where I'm trying to build off of something simple, something I can use in much more complicated situations in a lot of different freaking ways. Right? So the process we're about to set up is unbelievably useful in other areas of mathematics. So let's plot this crazy little function, square root of x plus 3. And then let's really focus near 1, because that's my near x equal to 1. So let's make the window -2 to 3. Sure, Jeff. And this would be -1 to 5. Let's see what that looks like. Alright, so there's my 1. Okay, cool. Okay, just enough time to do this one example. Alright. So what does it really mean then that as x approaches 1, this approaches 2? What does that really mean has to happen? It's sort of like what freaked people out about, remember horizontal asymptotes? And the weird thing about horizontal asymptotes is vertical asymptotes. Can you go through it?
No.
Hell no. Horizontal asymptotes, can you go through it?
Yeah.
Hell yes, all day long. And you saw examples like, no, Jeff. You saw examples like a function that would do this. But there are functions that would do things like this. We call that like damped oscillation. You pluck a guitar string. Thankfully, they eventually dampen out. They stop vibrating. If every guitar string didn't stop, that would be all. Please, God. But no more concerts. Stop it. Sorry. But this is interesting. I mean, you can go through that horizontal asymptote an infinite number of times. So what freaks people out about this is all that has to really happen, and you can't say it's got to. What do I want to say? People try to define this like it's got to get really close to it. But what does that really mean? It doesn't have to approach it from one side. It just all the values eventually have to be. And could this do this? Grow a little bit and then shrink a little bit and then grow a little bit and shrink a little bit. Would you still say that's a limit then?
Yeah.
You sure about that? This one, if it shrinks forever, if it shrinks and shrinks and shrinks, why am I saying that's officially a limit then? But if it shrinks and then grows, and shrinks and then grows, that's not a limit. I don't care if it's the average, I don't care. Because then you have the same problem as a sine function. What's the limit of sine as it goes to... Make a sine function. What's the limit of sine as it goes to infinity? What's the limit as it goes to infinity? It doesn't exist because it doesn't agree on anything. So if it shrinks and then grows and shrinks and grows, it doesn't agree. But what does that really mean to agree on something? What the hell does that mean?
It doesn't get infinitely close to zero.
Well, it does. So there has to be at some point, it never gets outside of some bounds. You see what I'm saying? At some point, at some arbitrary point, out. In this case, I'm going to infinity, so that's a little bit harder, but the idea is still true. At some point, at some value of x, let's call it x1. It never gets outside of this. And then a little further, it never gets outside of these. And a little further, it never gets outside of those. And that means that it's getting closer and closer and closer. Do you guys understand what I'm saying? So what we're... I already know. Shit. We'll get a little deeper into this next time. But what I call this distance here, I call that distance epsilon. Oh, yes. Epsilon. Oh, shit. More Greek.
Are the points you pick for that arbitrary?
Yes. Okay. So for any given epsilon, if somebody comes up and says, I want you to be within 0.07, I always have to find, and this is a bad example because I went to infinity, for our picture, if somebody says, so at 1, the limit was 4. So if somebody gives me some epsilon, so that would be around 4. So if somebody says, I want you to be within 0.1, I have to always be able to find, see how this works? It's not pretty. I will always be able to find some region that all my values will be that close to it. So if somebody wants to be even closer, this is going to have to shrink a little bit. Do you guys see the relationship? So somebody says to me, somebody gives me epsilon. They say, oh yeah, I want you to be, epsilon to be 1 over 18 billion. And then, and then we're like, all right, then I'll just make delta. Delta is this distance. I'll just make delta small enough so it does. All the outputs do fit in there. And if you really think about that, that makes total sense with what a limit should mean. I can get arbitrarily close to the limit if I restrict my x values. So that's what epsilon really represents. It's that arbitrarily close. Epsilon is whatever somebody wants it to be. Normally we consider epsilon to be small. And in fact, we consider epsilon to be the smallest positive number. But it could be anything, 0.1, 0.01. Epsilon normally wouldn't be 18 billion. That's kind of giving it something. I want you to be within 18 billion of my age. I think I could do that.
How do you find like absolute value of what? Or?
Oh, dude, yeah. So the last thing I'll say, and we'll do this example next time, is here's the official setup. To show this is true. This is the last thing we'll do. To show that the limit is that. Given epsilon greater than 0, we must find delta, and this is all in the book too, you might not have to read it, just read this. we have to find delta greater than 0. So given this, I want you to be this close to the value. We can find some region on the x values that will always be at least that close. We just find delta greater than 0. So that if, let me see if I can freak you guys out. Now what does that say? So my A is there. My A is the limit, right? So this says, what does this whole thing together mean? No. What does absolute value mean?
The distance.
Distance. So the distance between my x and my limiting value, right, has to be less than delta. So I want to be less than delta from A. That's all that really says. So that if I am less than delta from A, oh, don't you love this already? If I am closer to A than delta, some distance away from that, then my function values will be closer to L than epsilon. And you're all like, this is what I thought calculus is going to be. Freaky shit. Now please, dear God, how much have you studied this? Most of you, not much. So don't think you're supposed to understand everything I just said. My God, I can totally understand somebody out there. I have no idea what you said in the last 5 minutes. Oh, that's fine. I at least want to get this up there. Next time, I'll get a little worksheet. Don't forget also tomorrow is quiz. Quiz. All right.